Dear students, Assalamu alaikum. I welcome you to the 15th program on Software Engineering 1 course. For the last two programs, we have been discussing on the software design. In the last program, we discussed some of the design concepts such as what is abstraction, stepwise refinement, modularity, software architecture, and control hierarchy. In today's program, we'll continue our discussion on the remaining concepts. Today, we will discuss what is functional independence, what we mean by cohesion and coupling. Functional independence refers to the design of software such that each module addresses a specific subfunction of the requirements, and it has a simple interface when viewed from other parts of the program structure. As we discussed in our previous program, that whenever you develop a big software, the software is divided into a number of modules. Those modules interact with each other, and that interaction is shown with the help of a hierarchical diagram. Various functions make calls to each other, and the called function returns some kind of result back to the calling program. If the modules are independent, of course, they are easier to develop, maintain, and test. Of course, functional independence is a direct outgrowth of modularity, abstraction, and information hiding. Functional independence of modules can be measured using two quantitative criteria called cohesion and coupling. Cohesion is defined as the degree to which a module performs one and only one function. A well-designed module should do just one thing. That is, it should have high degree of cohesion. The modules that have low cohesion are difficult to understand, maintain, and reuse. A modules can have different level of cohesion as shown in this diagram. We start from level 1, which is lowest level of cohesion. We call it the coincidental cohesion. Then the next level is the logical cohesion. Then we have temporal cohesion, procedural cohesion, communication cohesion, informational cohesion, and functional cohesion. You can see from this table that coincidental cohesion is the worst kind of cohesion you can have. As you move up in the levels, then you go for a better level of cohesion. This shows that if a module has a functional cohesion, it is the best type of cohesion you can have, and that is the best design of a module. Informational cohesion, of course, is again a good type of cohesion. So as a designer, you should be striving for the modules which have the high level of cohesion. Now, it is very important to understand what is the meaning of these different levels of cohesion. We will discuss each of these levels of cohesion in detail with examples to clarify the concepts. So if you start from the lowest level of cohesion, which is called the coincidental cohesion, we say that a module has the coincidental cohesion if it performs completely unrelated actions. One example is here. We have written a module which takes some parameters and it performs some tasks here. Of course, we have not written the code here, but the comment clearly shows that some kind of code is written there. For example, this module has some statements written in some programming language which reverse the string, that means the parameter 1. Then it adds 7 to parameter 2, and then converts parameter 3 to floating float type. Of course, other similar tasks are there. Now, if you see all these tasks performed by this module, they have no relationship with each other. If you see, the reversing a string has nothing to do logically. Adding 7 to parameter 2 or converting parameter 2 to a different type. Now, these type of modules are not a good design, because if a module does various different types of things which are not related anyhow, these type of modules have then the coincidental cohesion. We should really be looking for the modules, as I just said, a module which performs a single task. In our case, in this example, we see that it performs various tasks which are not related to each other. Basically, what the programmer has done, he has simply divided his program into, let's say, he wanted to have 70 to 100 lines in each module. So he divided his program without any other logic than limiting the size of the module. When you have the modules like that, which perform various type of things, of course, you are not writing the correct type of modules. They have different type of problem. The major problem when you have the coincidental cohesion is that these type of modules are generally not reusable. They cannot be maintained, and they are even difficult to understand. If you look at the code of a module which performs various different tasks, and after every 50-20 lines, a new logic starts there, these type of programs are, of course, very difficult to debug and understand. So having the coincidental cohesion in a module is not something we are looking for. We should be looking for a better level of cohesion in a module. The second type of cohesion is what you call the logical cohesion. We say a module has logical cohesion if it performs logically related tasks, and the calling program calls the module and selects one of the tasks from that module. One very good example of a module which has the logical cohesion is our module called the trigonometry. It takes two parameters, the int parameter option and a parameter val of float type. Then inside the module, the code is written to calculate different trigonometric function. For example, if the value of the option is 1, then here we write a complete code to calculate the sign of that value. If the calling program passes 2, that means the option value is 2, then it means the calling program wants this module to calculate the cosine of the value, and similarly the other things. Now, if you see why this happened, or why a programmer selected to put all these functions into a single module, then you might notice that his logic was that all these functions are basically the trigonometric function. So they have a logical relationship. That tempted him to put all these functions into a single module. So when a module has a logical cohesion, of course, these type of modules are again very difficult to maintain. Not only they are difficult to maintain, but the interfaces become quite complicated. The user has to know the internals of the code. That means user should know that if he passes the value of option 1, then this part of the code which calculates the sign of a value will be executed and the function will return that value. So the programmer has to know the internal logic of the program, which is against the concept of the information hiding and the abstraction. A function should basically, if we recall, that we are saying that a function should do a single thing. So if a function has the logical cohesion, we say yes, it is doing related thing, but again, this is not a good module. Reason being very simple. These type of modules are difficult to maintain. These type of modules are difficult to reuse, and they have very complicated interfaces. The next level of cohesion is called the temporal cohesion. We say a module has a temporal cohesion if it performs tasks only because they occur in a sequence. Here is one example. We have a module, call that module initialization module. What this module basically does, it opens different files, it initializes some global variables, and again, the reason for putting all these things inside the module was that from the programmer point of view, he wanted to make a single call to a module which will initialize all the variables and open all the files and initialize all the files. So this type of cohesion, when you put the task inside a single module, which have some kind of relationship here, that they have to be performed at the same time, then we say the module has the temporal cohesion. The next level of cohesion is called the procedural cohesion. When a module performs actions related by sequence of steps to be followed by the product, or when a module basically implements an algorithm step by step, then we say the module has the procedural cohesion. An example of a procedural cohesion is given here. You can see we have a module, my search. Inside the module, we have written the code which loads a file or opens a file. Then it does a search for a specific record in the file, and then it prints the result of that search. Now, if you see here that what's really the programmer has done, he has basically written the procedure or a module following the logical steps of the algorithm. Of course, you cannot do the search unless you first open the file. Once the search is complete, then you can print the result of your search. Now, it's very important to understand the difference between the temporal cohesion and the procedural cohesion. In the case of temporal cohesion, we perform a series of steps, but their sequence may not follow some specific algorithm steps. But in the case of procedural cohesion, we write our procedure or a module step by step as mentioned in our algorithm. When a module has procedural cohesion, similar to the temporal cohesion, this type of cohesion creates different problem in the modules. Of course, the major problem is that these type of modules are unlikely to be reused. They are difficult to maintain as well. The next high-level cohesion is called the communication cohesion. The communication cohesion is defined as when a module performs a series of actions on the same data. That is, the module takes some parameter from the calling module, then it performs a series of actions on the same data. For example, here we pass a string to this function. This function first reverses the string and then converts the string to the uppercase. So here we are performing two separate tasks. That means reversing the string and converting the string to the uppercase. Again, the reason behind putting these two actions into a single module has been that in the view of the programmer, these actions have to be performed on the same data, therefore they should be in the same module. Of course, this type of arguments will not produce a well-defined and well-designed module. Now, if a module has the communication cohesion, still we have the same kind of problems. The problems are that again, these type of modules are very difficult to reuse. They are difficult to maintain. And whenever there is a problem, then they are difficult to debug as well. The cohesion level above the communication is called the informational cohesion. The informational cohesion is defined as when the module performs a number of actions on the same data structure, each action with its own entry point and independent code, just like when you write a class in an object-oriented programming language. A module which has the informational cohesion is shown here. We have written a module's sales table operation. Some of the data structure is defined, just like we define the variables in a class, and then we have various functions written inside that modules, and each function provides different functionality. So each function basically is the entry point into the module. Whenever a calling function wants to use whenever a calling module wants to perform one of the tasks from this module, it makes a call to a specific function in this module. That call is of course made by using the name of the entry point. In the case of a class, it might be the name of a method. So a calling program will call that method, and that method will be executed. Once that method completes, of course, it exits and we go back to the calling module. As you can see, a module with informational cohesion is essentially an implementation of an abstract data type. The best module should exhibit what we call the functional cohesion. And the functional cohesion is defined as when a module performs exactly one task, then we say that module has the functional cohesion. Here is one example. We have written the module mySign. It takes one float parameter, and of course here we have written some code which will return the sign value of the parameter. So that's the type of module we should be looking for. So whenever you have a module, you should look for what type of cohesion that module exhibits. If that module exhibits temporal cohesion or the low level of cohesions, then the best way is to break up that module into sub-modules in such a way that each module or the sub-module you have created performs a single task. A module which has the functional cohesion has many important characteristics which are very, very important in developing a quality software. For example, the modules with functional cohesion are easy to maintain, they are easy to reuse, they lead to fault localization. That means whenever your software misbehaves, you can easily find out the code that actually has that fault, and you can correct or debug that code quite easily. These type of modules are also easy to extend. You can easily improve the code of that single module. The second measure that we use to determine the functional independence of module is called coupling. Formally, coupling is a measure of relative independence between modules, or the degree of interaction between two modules. Now here you should see one clear difference between coupling and cohesion. Cohesion is basically how good a single module has been written. So cohesion is related to a single module. But on the other hand, the coupling basically tells us that how different modules that we have developed interact with each other. So a best design should be a design where you have a high level of cohesion but we should try to minimize the coupling, that each module should do its work as independently as possible. Now, coupling, of course, depends on the interface complexity between modules, the point at which the entry or reference is made to a module, and the data that is passed across the interface. The actual data that is passed in and out of the module should be kept to a minimum. A well-partitioned system has a very low coupling, as I just said. Similar to cohesion, there are different levels of coupling as shown in this table. From the lowest level of coupling, what we call the content coupling, we have common coupling, control coupling, stamp coupling, and data coupling. Now, you can see from this table that if the modules have the content coupling, that's not a good design. It's a bad kind of design. And we should be looking for a higher level of coupling. The best could be the data coupling, which is the best type of coupling the modules could have. Now, let's discuss these different levels of coupling in little more detail. So let's start with what the lowest level of coupling, which is called the content coupling. We say two modules are content coupled if one directly references the contents of the other. That's the worst kind of coupling you can have, that we have one module which directly interacts with another module anywhere in between that module. Now, for example, if a module modifies a statement of another module, that seems very awkward, that how a module or one function can change the statement of another function when it is executing. But it was possible, and it is possible. For example, COBOL allowed modification of statements. Assembly language even allows no. If the memory protection is not there, then the one module can go inside the area of another module, can change its data, can change even the statements. Once these things are done, then of course the second module will start behaving incorrectly. Therefore, this is the worst kind of coupling you can have. Good thing is that most of the modern programming languages don't allow one module to change the statement or the data of another module unless you have defined that data as the global data. The next type of coupling is called the common coupling. Common coupling is defined as that when modules have access to the same global data. In programming practices, we always say that we should not use the global variables because of the side effects. Of course, in some cases, there might be no other way but to use global variables. But what's important here to understand, we should try to minimize the use of global variables. They are not a good programming practice. So we say two modules are common coupled if they have access to the same global variables. And remember that if one module makes a change in the global variable, then all the other modules which are accessing the same data will also be affected. That thing should be kept in mind when you are using the global variable. The next type of coupling is called the control coupling. We say two modules are control coupled if one passes an element of control to the other module to explicitly control the logic of other module. Now, here are two modules which have the control coupling. We have module A, which makes a call to module B, and module B takes two parameter option and a float. Now, if you remember, this is the same module we used in the logical coupling, in the logical cohesion. This module has the logical cohesion because it performs various different tasks which are logically related. And the calling program will control which part of this module should execute. For example, in this case, when module A makes a call to module B, then of course the parameter which is passed is 1. That means this part of the code will be executed. Ultimately, it will lead to the control coupling. The next type of coupling is called the stamp coupling. Stamp coupling is defined as if the called module uses only some of the components or information of the data structure passed by the calling module, then we say those two modules have the stamp coupling. Here is one example of the modules which have stamp coupling. For example, we have a module A which makes a call to module B and passes a parameter student1, where student1 is basically a structure you have already defined with various fields such as student ID, student name, date of birth, etc. Now, when this whole structure is passed to module B, and if you look at the code which is written inside module B, then you will notice that this module is basically using only the part of that structure. That means use only the field, marks, and grade of the structure, and nothing else is used in this module. The next level of coupling is called data coupling. We say two modules are data coupled if all arguments are homogeneous data item. There are two examples here. These are, we have just shown the calls which are made to the second module. Now here is a call which is made by, let's say, module A to the second module, display time of arrival. And you see here, the calling module is passing only a simple data, flight number, which might be an integer, a non-decomposable data type. And the second module returns the or displays the time of arrival of that flight number. No extra data is passed, and all the data which is passed by the calling module is used by the second function. The second example could be a module B, which basically finds the maximum number in an array. Here you can see the calling module passes a complete data structure, an array, to the second module. Now the second module, of course, is going to find the maximum value in that array. That means the whole array will be used by the second module. So whenever you have these type of modules which pass only the data which are of simple type or the data structure which is going to be entirely used by the second module, then we say that these modules have data coupling. In the next program, we'll continue our discussion on software design, and we'll discuss how the data design and architecture design of a software is done. Till then, good luck and Allah Hafiz.